Swayam Prabha. Digital India. Educated India.
We will continue with the introduction to micromachining processes. In the first couple of lectures, I have already discussed. What I have discussed is about my introduction to micromachining, definitions of the micromachining and classification of the micromachining. As you recall, I classified in two categories this micromachining processes. One is the traditional micromachining processes, which includes micro turning, micro milling, micro drilling, etc. Another was the advanced micromachining processes, which were of three types. As you can see here, mechanical type micromachining processes, thermal type micromachining processes, electrochemical type of micromachining processes, which includes chemical as well as biochemical micromachining processes. And if you recollect, we further classified mechanical type of micromachining processes as abrasive jet micromachining, abrasive water jet micromachining, ultrasonic micromachining and water jet micromachining processes. These are the advanced mechanical micromachining processes. Now, micromachining and the same have been given again here as the micro turning, micro milling, micro drilling, etc. And then these are the total advanced micromachining processes, which includes thermal, mechanical, electrochemical and chemical type. I just repeat them as micro EDM, micro ECM, micro AJM, micro LVM or LVM as such, and micro EBM and micro ultrasonic machining and so on. There are large number of advanced micromachining processes. Some of them we will discuss later on in detail. Now, in this lecture, I am going to talk about the working principles of different kinds of micromachining processes overall, which includes both all the three types, mechanical, thermal and electrochemical and chemical type of micromachining processes. First, we will discuss mechanical types of advanced micromachining processes, especially the working principle and some of the applications of the same. Now, principle of advanced mechanical micromachining processes. What is the mechanism of working of these processes? I will take up one by one. As you can see here, this is the schematic diagram of the setup for abrasive water jet machining process. Now, you can clearly see here there is a inlet for the water coming from here. It comes at very high velocity, we will discuss it later, and then there is a joule through which it is coming out, and from this particular end, as you can see here, abrasives are being fed into the jet of the water over here, and this is known as mixing tube. In this mixing tube, water abrasive particles get mixed up with the water, and this moves downward, and here is the jet coming out the mixing tube, and this jet consists of water as well as abrasive particles, very fine abrasive particles which may be of micro or nano size, and the velocity of these abrasive particles is as high as 800 to 900 meter per second. So, you can calculate the kinetic energy of each particle moving at such a high velocity. Now, this is the real life application of abrasive water jet cutting. You can see this is the jet coming from there, and this is cutting the plate being cut over here, and here is the jet coming out after cutting this particular workpiece or the plate, you can clearly see visible over here. Now, there is another process, again important process known as ultrasonic micromachining or ultrasonic machining process. Now, you can see here, this is the tool and this is the workpiece and this is the cavity being machined. Now, and there is a gap between the tool and the workpiece, as you can see here, this is the gap. In this gap you have the slurry. This slurry contains the water and very fine abrasive particles. When this slurry comes in, this tool is vibrating at ultrasonic frequency, that is around 20,000 vibrations or 20,000 hertz per second. So, with such a high vibration frequency, each abrasive particle in this particular gap is hit by the tool, and you when this is hit by the tool, it moves towards the workpiece with a certain high kinetic energy. Because of that high kinetic energy, each abrasive particle is able to remove the material from the workpiece, and you get the replica, inverse replica of the tool as the cavity formed over here. You can see clearly this is the cavity formed on the workpiece. Now, so size of the abrasive particles, velocity with which they are moving or the kinetic energy, type of the fluid, water or air, we will see the application of air also. All this determine the material removal rate from the workpiece. Then you have abrasive jet machining process, as you can see here. Here in this particular case, abrasive water jet machining, we are using water as the carrier fluid. Now, in this particular case, abrasive jet machining, air is used as a carrier fluid. So, what is done here is that abrasive, very fine abrasive particles, they are mixed with the air, and that abrasive air jet comes out of the nozzle, as you can see here, and this jet hits the workpiece surface, and depending upon the kinetic energy of each abrasive particle, the material is removed from the workpiece and you get certain cavity formed on the workpiece surface. This cavity size and shape depends upon what is the gap you are maintaining between the bottom of the tip of the nozzle and the surface being machined on the workpiece. As you can see here, this is the initial gap between the bottom of the nozzle and the top surface of the workpiece. After machining, this is the shape which has been machined with the help of this particular one. Now, depending upon the gap, this gap, you can see the features of the cavity being formed are changing. As you can see in this different cases, the size of the cavity or width of the cavity is continuously increasing. In all the cases, as you are increasing the gap from 0.75 millimeter to 1 millimeter to 1.5 millimeter and 2 millimeter. So, this also decides the accuracy that you are going to get. Now, the question is how the material is being removed in all these three mechanical type of advanced micro machining method. Now, we have two kinds of material, one can be the ductile material, another can be the brittle material. So, the mechanism of material removal in both these materials is different, does not matter whether it is abrasive water jet machining, ultrasonic machining or abrasive jet machining. Now, you can see here in this particular figure, if the abrasive particle is hitting the workpiece surface at a certain angle, not 90 degree, rather than less than 90 degree, and the workpiece material is ductile, then you can see in this particular case two forces are acting. One is the normal force, which is Fy, which is responsible for the penetration of the abrasive particle inside the workpiece, and there is another force Fx, which is responsible for removal of the material in the form of the micro nano chips, and it is the shearing force which is shearing the workpiece material and removing the chip in the form of small materials from the workpiece. If it is a brittle material, then the mechanism is slightly different. Here in this particular case, as this abrasive particle is hitting the workpiece, it is a brittle material. So, what happens initially, micro cracks initiates and it spreads all over the area which is being affected, and you have the lateral cracks and little bit of plastic zone is there, and you can see that here the cracks are expanding, and finally, this is removed in the form of the micro nanochips from the workpiece. So, two mechanisms, one for ductile material, another for brittle material, are quite different from each other. So, forces acting on each particle and particle size will decide the scale of material removed. But another thing is, this can be used to cut at macro level, micro level or nano level, depending upon the forces acting on each abrasive particle and size of the abrasive particle. Now, let us discuss little more details of these processes, that is abrasive jet machining process. As you can see here, this is the abrasive jet machining process, this is the nozzle, and different kind of the features are being created on the plate with the help of this particular process, and you can see this hole is created, here the hole is created, and different features are being created with this particular process. So, the abrasives used are normally alumina, Al2O3, silicon carbide, glass beads, sodium bicarbonate. Which abrasive should be used depends upon which workpiece material you are going to machine. The abrasive particle hardness should always be much greater than the workpiece material hardness. That makes a difference in the form of the accuracy and the material removal rate you are going to get. So, composition, strength, size, mass flow rate, etc. of this abrasive particle decides the process performance. As long as carrier is concerned, in case of abrasive water jet cutting, as I mentioned earlier, you are using water as carrier, but in case of abrasive jet machining, you are using normally the air or nitrogen or CO2 gas as the carrier. Their composition, pressure and velocity also affect the performance of the process, because pressure or the velocity of each abrasive particle will decide kinetic energy, and kinetic energy will decide how much deep it can penetrate inside the workpiece and remove the material. In case of ultrasonic machining, it is the pressure with which the horn or the tool is hitting the abrasive particles, which will decide the kinetic energy again of that particular particle and the material removal rate. Now, the nozzle is normally made of tungsten carbide, sapphire or other very hard materials. The geometry, material, stand-off distance, feed rate and inclination to the workpiece or the inclination of the nozzle to the workpiece will also affect the performance of the process. Now, here stand-off distance, as I have mentioned to you earlier, that it is the distance between the bottom of the nozzle and the surface of the workpiece which is being machined. And as we have seen in case of AJM, I have told you and I have shown you, it has big effect on the shape and size of the cavity being machined. It gives the features or rather the parts of the AJM setup. As you can see, gas supply cylinder is there. You have the pressure regulator, with the help of which you can regulate or control the pressure with which the gas is being supplied, and filter is necessary, so that clean air or gas goes into the system. Then you have vibrator, so that air and abrasive particle can very nicely mix with each other, and that is done with the help of the vibrator, and you have power supply and mixer is over here, which is being vibrated with the help of the vibrator. Then you have food control valve, so that how much air should go into the nozzle, that can be controlled with the help of the food control valve. And here is the nozzle, and you can see this is the mixture of the air and abrasive particle is coming out, and the nozzle is inclined at a certain angle to the workpiece surface, top surface of the workpiece, from where you are going to remove the material. And after hitting the workpiece surface, this abrasive particles, they bounce back and go away from the cavity being machined. It does not go and hit the other machines or other persons working over there. You have the hood over here, so that it will stop them, and whatever air or gas you want to exhaust outside the machining room or machining chamber, this will go out from here. Now, you have the abrasive jet micro machining applications. As you can clearly see here, the cross sectional view of the machine surface, cavity over here. This is the shape and size of the cavity after one pass of machining. Now, if we continue, and you can see the magnification here, this is 100 times magnification over here, and if you see this, it is the cavity you are getting after 11 passes, and you can clearly see the difference between the two, and the magnification over here is 200 micrometer is this particular length. As you can see, it is 55 times, it is 150 times. Now, another process which can be used for micro cutting or cutting both is the water jet machining process or water jet micro machining process. The principle remains the same. Here the kinetic energy of water is used to remove the material. Definitely it is not used for cutting very hard material. Initially water jet machining was developed for cutting the coal mines in the Japan, because so many accidents were taking place by fire in the coal mines, and keeping that in view, water jet cutting process was developed, so that fire does not take place in the coal mines. Now, you can clearly see this is the nozzle, and here is the jet of water, and this is the plate being cut, and this is the exiting jet of water, and you can get very good shape and size by cutting it. Now, if you convert this, or if you have the size of the nozzle or diameter of the inner diameter of the nozzle in microns, few hundred microns, then the cut or the feature that you are going to create, that will come in the category of micron size features or micro machining. These are the different elements of the water jet machining setup. Fluid supply is there, and it is having the filter. Then you have the pump, with the help of which you are achieving a certain pressure of the water when it is supplied through the nozzle, and this water pressure is quite high, and you have the intensifier to increase that particular pressure, and accumulator is there where you collect the water, and then you have the control, with the help of which you can control the pressure or other quantity of the water that you are going to supply to the valve, and then you have the sapphire nozzle, and this is the jet of the water which is coming at very high velocity, and it is the workpiece being machined with the help of this particular water jet. And when it is coming out, it should be drained at a safe place, or because it is to be recycled again and again, it is to be used, hence you have the drain over here. So, you can again see water jet there. Now, then you have another process which is very useful process, that is known as abrasive water jet machining process. It is a modified version of water jet cutting, because water jet cutting has certain limitations. It cannot machine very hard materials and very thick materials. So, researchers, scientists, what they did, they mixed the abrasive particle with the water jet, so that the kinetic energy of abrasive particle is used over here for cutting certain type or all kinds of materials you can machine. Very hard materials are being machined with this particular process. This is the same setup which I have a schematic diagram of the abrasive water jet cutting, which I showed you in the earlier slide. Inlet water is there, abrasive inlet is there, mixing tube is there, and jewel of the nozzle is there. Now you can see the similar kind of the things. The jet is coming out after cutting this particular composite plate, and this is the nozzle, and this is for abrasive particles going in the mixing chamber. Now you can see clearly here important thing, that if you have the low feed rate, then you can get a good surface of the machined or the cut surfaces, good characteristics of the machine surface. If it is you have a medium feed rate, then you can get the hashing or the lining over there, because feed rate is indicated here. If it is very high feed rate, then the surface obtained is quite rough, as you can see over here. So, one has to decide carefully what kind of surface they need, and accordingly they have to decide the feed rate with which you are feeding. Now, another mechanical type of micromachining process is ultrasonic micromachining. Basic elements of ultrasonic micromachining: ultrasonic power supply, then you have the ultrasonic transducer, third one is the tool holder, and then you have the tools and abrasive particles. Now, basic elements of the USM are shown over here in diagrammatically. You can see here, this is the electric power generator, transducer is there, which converts electrical energy into mechanical energy. Here is the mechanical amplifier, and then a whole sonotrode, and this is the tool. Now, depending upon the shape of the tool, you are going to get the shape of the cavity being formed on the workpiece. Here is the workpiece, and this is the slurry being supplied by the pump, with the help of the pump from the slurry tank, and as the ultrasonic machining starts, you get the cavity. Here very hard workpiece material can be machined, and complicated cavities can be produced on the very hard workpiece materials. This is the beauty of this particular process, and the constraint is, or the requirement is, that whatever complicated shapes and sizes you want to produce on the workpiece, first you should be able to produce it with high accuracy on the tool, then only it can be replicated. Then what are some of the applications of ultrasonic micromachining? You can use it for drilling micro holes. The amplitude of vibration in this particular case is 5 micron. Workpiece material is silicon, which is very hard. Tool material is tungsten, and then the tool size varies from 50 micron, 100 micron, 150 micron, depending upon what is the size of the hole that you want to make. And then you have the abrasive grain type. You can use different kind of the grains. The requirement is that the grain should be much harder than the workpiece material hardness, otherwise it will not work. So, in this particular case, they have used polycrystalline diamond powder as the abrasive particles. You can use other abrasive particles also, as I mentioned earlier, alumina, silicon carbide, tungsten carbide, etc., depending upon the hardness of the workpiece. Then size of the abrasive particle 1 to 3 micrometer, it controls the accuracy and the surface finish also that you are going to get on the machined surfaces. And then total tool feed is 515 micrometer. It depends upon the depth that you want to achieve of the hole or the cavity being machined. The ultrasonic micromachining generated micro hole diameter 61 or 66 micrometer. You can see over here, this is the scale of 10, and you can see nice surface or the nice surface of the hole produced. Then you can use it for creating the cavity other than the hole, as you can see over here. This is a very good square cavity with kind of non-circular pillar over there. As you can see over here, this has been produced with the help of the ultrasonic micromachining process, and you can see the size of this, dimensions of this are very very small, because this scale is given as the 100 micrometer. So, you can calculate the size of this particular cavity being produced by this one, and here are the machining conditions given. Important thing is the gap between the workpiece surface and the bottom of the nozzle is 6 micron. Now, merits of the ultrasonic micromachining: you can have machining of any material regardless of their electrical, thermal, magnetic conductivity or their other physical properties. As we can see, ultrasonic micromachining apply to machining semiconductors also, such as silicon, germanium, etc. Ultrasonic micromachining is suitable to precise machining of brittle materials, and it can drill circular or non-circular holes in any or every, it should be every rather than very hard materials, any hard materials or very hard materials, both are correct. And we have seen one non-circular hole also in the earlier slide, which was a square hole, and less stress because of its non-thermal characteristics. Now, what are the demerits of ultrasonic micromachining process? Ultrasonic micromachining has low material removal rate as compared to other advanced micromachining processes, and tool wears fast in ultrasonic micromachining because tool is directly hitting the abrasive particles. So, it is in direct contact with the abrasive particles, it is applying the force, so that it also wears out continuously, and machining area and depth are restrained in ultrasonic micromachining, because this is normally used for small size and shapes being machined on the small workpieces rather than very large workpieces or very large features or cavities being machined. Now, another class of advanced micromachining is the thermal advanced micromachining processes. Now, in the mechanical type of advanced micromachining processes, material removal was due to the mechanical forces, as we have seen in all the cases. Does not matter whether it is water jet machining, abrasive water jet machining, abrasive jet machining or ultrasonic micromachining. But this may not work all the time very well. So, scientists evolved thermal advanced micromachining processes, where the basic principle is that the material, workpiece material is heated, melted, and part of it may get evaporated, and then the molten material is thrown out or removed from the cavity. So, let us see just basic principle of these advanced thermal advanced micromachining processes. First, let us take electrical discharge micromachining processes, and then second category is beam micromachining processes, which includes laser beam micromachining, electron beam micromachining, and third is ion beam micromachining. Ion beam micromachining is normally put in the thermal micromachining processes category. However, personally I do not agree with this, because in this particular case there is hardly any heat generation, melting and vaporization is there of the workpiece. Hence, it should have been more correct to put it in mechanical type of advanced micromachining processes, but as the practice is there, I have also kept it in the thermal advanced micromachining processes group. So, let us see what are the different types of beam micromachining processes and what is their working principle. Ion beam machining process. Now, you can see here is the liquid metal source from which ions are detached, and here is the extractor this one, and you have the lens, and this ion are coming out and they are moving through the aperture. Depending upon the size of the aperture, the size of the ion beam is governed, and you have the deflector plate. This plate moves this ion beam either on the left side or the right side for exactly locating the beam on the workpiece surface, and then you have again the lenses which are concentrating this particular beam, and then the beam is coming and hitting the workpiece surface over here, and depending upon the size of the beam you can cut the material feature, the feature on the materials, and this particular process is normally used for nanomachining, but micro features also can be machined over there with the help of this particular process. You can clearly see here that here is the primary ion beam which is coming, which is shown over here, and this beam is coming at an angle and it is hitting the workpiece surface or the sample surface, and theoretically it is assumed that each ion will hit an atom or one atom and throw it out from the workpiece surface, but normally this control of the energy of the ion is comparatively difficult. So, it has much larger energy than what is the bonding strength between the two atoms, and one ion is able to remove more than one atom from the workpiece surface, and they are thrown out from the sample or the workpiece surface, as you can see here, and depending upon the energy contained in each ion, the number of atoms thrown out from the workpiece surface is decided. There is another category of beam micromachining processes, that is electron beam micromachining or electron beam machining. Again it is used for removal of the material at the micro level only or nano level, not at macro level or meso level. Now you can see here electrons are emitting from the cathode, attracted towards the anode over here, then here is the electron beam is there, you have the focusing coil over here, and this is being focused on the workpiece. With the help of the deflection coil you can slightly move on the left or the right or forward or backward, and exactly on the location where you want to create the feature the beam is concentrated, as you can see here. Now vacuum pump is being used. This is very important to note that mostly this is done under vacuum, but in some cases scientists have found that it can also be used without creating the vacuum over there. We will discuss it later on when we discuss details of electron beam micromachining process. Now third very important process is known as laser beam micromachining, and laser light is used for melting and vaporization of the workpiece material. Now here you can see this is the long pulse laser beam is being used over here. This is the laser beam, it is hitting the workpiece. When you are using the long pulse laser beam, then many kinds of the defects are created in the machine cavity, as you can see over here. These are the debris etc. being formed, this is a recast layer, and so many other defects are there. We will discuss them in detail when we are discussing laser beam micromachining, but where you want very high accuracy, in those cases you can use the short laser pulse by micromachining, and you can see clearly here this is the cavity being machined and here this is the cavity being machined. So you can see different kind of the defects created over here, while in this short laser pulses there are hardly any kind of the defects created in the machine cavity. Now, so this is a short pulse laser machining. Now, very commonly used process, that is known as electric discharge machining process, and this process is being used even in the small scale industries and medium scale industries. Definitely it is used in large scale industries also, and the working principle is very simple. You have the tool as the cathode and workpiece as the anode, and you have the dielectric between the tool and workpiece, and that is known as the gap between the tool and workpiece is known as interelectrode gap, and dielectric is flowing at high velocity, and when the breakdown voltage is there, then the plasma channel is formed as shown over here, and material from the tool is removed due to the melting and vaporization, and material from the workpiece is also removed due to the melting and vaporization. So, you can see the crater formed on the tool as well as crater here is formed on the workpiece also, and depending upon the shape and size of the tool, you are going to get inverse replica of the tool on the workpiece. However, it is not exactly the replica, there are the size of the features created on the workpiece are always larger than that on the tool. We will discuss all these things in the detail. The column is normally of 100 microns, but all this depends upon what is the dielectric being used over there, what is the breakdown voltage and so on. Now, let us see more details about electrode discharge micromachining process. Basics of EDMM, that is electrode discharge micromachining process. In EDM, material is removed by the thermal erosive action. In electrical discharges, that is mainly we are using here is sparks, not the arc really speaking. If you want to have a good surface finish, good accuracy, then it should be the spark, and discharges should be avoided as far as possible. Otherwise, it may lead to the arc, and if arc is there, then your workpiece may get damaged. Provided by the use of pulse generator, here you are using the pulse current rather than the continuous current. The same principle of EDM is applied to remove material at micro level for micromachining. In this particular case, when we are talking of micromachining, the size of the tool is in the micron range rather than in the macro range, and that is how you are going to get micromachining in EDM process. In micro EDM, the key is to limit the energy in the discharge or the spark, because depending upon the spark energy, the amount of material to be removed from the workpiece will be decided or controlled. Hence, the spark energy is to be controlled, especially in case of micro EDM process. Here is the diagram of EDM process. You have the power supply, controls are there. Negative is always the or cathode is always the tool, and anode is always the workpiece over here, and you have the dielectric fluid. The dielectric fluid is normally used earlier, it was the kerosene which was used as the dielectric fluid. Nowadays, manufacturer of the EDM machines, they supply their own dielectric fluid, and most of them do not tell really what is the composition of this dielectric fluid. However, nowadays deionized water is also used as a dielectric fluid. We will discuss them while we discuss the electric discharge micromachining process. And here is the workpiece, and you can clearly see the cavity being formed over here is shown over there, and it is the replica of the tool over there. You have the filter, because this dielectric is recycled, it is used again and again to a certain extent. Hence, you have the filter over there, pump is there, and dielectric after being used once, it comes to the dielectric fluid reservoir. Here you have the different filters at different locations which filter this one and clean this dielectric before resupplying it. And you can see clearly here is the cathode and here is the anode, and between the two spark is taking place, and depending upon the gap between the two, means cathode and anode, that gap is known as inter-electrode gap. The intensity of this spark is also decided depending upon the gap also. The spark created deliberately in this particular process, heat in the localized area is produced. As you can see over here, I have shown you this type of the picture earlier also to you in the earlier slide. Here you can clearly see the few hundred of micrometer is the inter-electrode gap in case of macro EDM, but in case of micro EDM it is few tens of micrometer as the inter-electrode gap. And you can see the melting and or vaporization. Because of that, you have the crater over here formed over there. Now, input parameters to the EDM electric discharge micromachining process are voltage, capacitance is controlled, layer depth is decided by what are the input parameters including the feed rate. Now, you have the micro EDM machine and output is normally the material removal rate, but as I mentioned earlier, tool is also varying. So, electrode wear rate is also there, which is quite important to understand. Otherwise, if tool gets deformed, reshaped, then you are not going to get the correct cavity on the workpiece surface, and you have to control the gap, that is the inter electrode gap also, to get the correct cavity on the workpiece, and that is the output. So, you can see here electrode wear rate versus capacitance, and as the capacitance is decreasing, electrode wear rate is increasing to a certain extent, say up to 100 picofarad, and then it starts decreasing again. Then you can see the material removal rate, as capacitance is decreasing, material removal rate is also decreasing. Now, here you can see layer depth is in terms of microns, and here is the material removal rate. So, you can see for different picofarads as the capacitance, the performance of the EDMM process is different. And then for slot machining, again you have the different voltages. As the voltage is increasing in the up to say 200 volts, you are getting higher material removal rate, but somehow at 80 volts the material removal rate is lower at certain feed rate, and then it starts increasing. So, what are the scientific reasons for all these things? We will discuss when we discuss EDMM in detail. Now, distinguishing features of the electric discharge micromachining process is that it is able to machine any electrically conductive material irrespective of their hardness, because in mechanical type of advanced micromachining processes, it is the hardness of the workpiece which controls the performance of the process, and that is why scientists had to find alternative processes whose performance is independent of the mechanical and physical properties of the workpiece, and EDMM was one of them. And then machining can be done without applying pressure on the material. No mechanical pressure is being applied on the workpiece material, with high precision on curved surfaces, inclined surfaces, and very thin sheet materials which are difficult to drill or machine. So, this particular process can be used for any kind of complicated surfaces, curved surfaces or inclined surfaces. However, the performance is also affected. What is the shape of the surface being machined? We will discuss this later. Now, high aspect ratio can be achieved in electric discharge machining, micromachining processes also, as in case of electric discharge machining. Then let us see some process variables which compare EDM and EDMM process. I will not go into detail over here, but I will just give you an idea about this. The mechanism of material removal in both the cases remains the same, whether EDM or micro EDM. Material removal rate is definitely different. It is much higher in case of EDM process, as you can see over here, 3 into 10⁵ cubic millimeter per hour, while it is 0.6 to 6 cubic millimeter per hour. Dimensional accuracy is 10 to 50 micron in case of EDM and 3 to 1 micron in case of micro EDM. Surface finish achieved is 0.2 to 2.5 micrometer in case of EDM. This is if I understand correctly, RA value, and in case of micro EDM it is 0.4 to 0.5 micrometer. So, you can get good surface finish in micro EDM compared to EDM process. Power consumption is comparatively low, 2 to 4 kilowatt hours in case of EDM, but in case of micro EDM it is low. Tool material that you can use, the basic condition for the tool material is that they should be electrically conducting material. So, you can use copper, brass, copper tungsten alloy, silver tungsten alloy, graphite, etc. Nowadays people are trying to use more commonly the graphite rather than metals as the tool material, but graphite also has its own constraints. We will discuss them in detail later. Tungsten electrodes up to 0.1 diameter, 0.1 micron diameter smaller sharpened in the machine up to 20 micrometer, and gap normally kept is 125 or hundreds of micrometer in case of EDM process and tens of micrometer in case of micro EDM process. Though this gives the range of both EDM as well as micro EDM processes, the gap is concerned. Now, comparison of EDMM processes, you can clearly see. I am not going to discuss detail over here, but here are the micro EDM operations like die sinking operations are there, and micro buyer EDM operation is there. Feature being created circular, and then slot is there, and then feature size is in terms of millimeters are given over here, and dielectric different deionized water etc. This should be in terms of micrometer rather than feature size in terms of millimeter, and then material is over here, and the thickness we used like this, and machining time is in terms of second. You can see depending upon the size of the feature you are creating, the machining time will be controlled, and here it is the material removal rate rather than RR, M is missing over here. You can get different material removal rate depending upon the conditions under which you are micro machining. Now, power supply in EDMM, the power supply is simple and rugged. It is very reliable and suitable for higher frequencies, low cost, and competitive for small energy control for micro machining processes. These are the some of the characteristics which the power supply should have for micro machining, electric discharge micro machining processes, and this is the relaxation circuit type power supply over here, and you can see here it is the input voltage or supply voltage, resistance is there, capacitance is there, and you can see it is connected to the tool which is working as the or which is acting as the cathode, and here is the workpiece which is acting as the anode, and this is the gap between the two, and you are supplying the dielectric over here, and you can machine the cavity as you want. Now, in some cases wire electric discharge grinding process is here which is used for produce very fine electrodes. Here this is the workpiece which is being machined to create a very thin electrode or few hundred micron size electrode or few tens of micron size of electrode. This is the wire which is used moving continuously and used to remove the material from the workpiece through EDMM principle, that is melting and vaporization. You can see some examples of electric discharge micro machining. Here is a 30 micron shaft and 50 micron holes produced by micro EDM. This is the shaft being produced, and the diameter of this shaft is around 30 micrometers, and the hole produced over here is of 50 micrometer. Please note that the magnification here and here are different from each other, do not get confused. Now, holes as small as 6.5 micrometer in diameter and aspect ratio of 7.5 have been produced. This is the 6.5 micrometer, this is 8.5 micrometer, 10.5 micrometer and 12.5 micrometer. So, you can produce the holes of different dimensions and different depth depending upon a requirement using electric discharge micro machining process. There are some more examples of electric discharge micro machining process. You can see 50 micron electrode, end view is there, and this is the 6 micron diameter electrode produced by EDMM process, and you can see 22 micron diameter hole drilled with 6 micrometer electrode. Now, as I have mentioned already, the feature created or the cavity created in EDMM process is its dimensions are always larger than the dimensions of the electrode, and how much larger, it depends upon the input machining conditions under which electric discharge micro machining is being done. So, you can see here 68 micron wide slot drilled with 50 micron electrodes. So, electric discharge drilling using solid electrodes over here, these two I have mentioned to you already. examples of EDMM. One more example, this is the complicated part being machined over here. You can see this is the part which has been machined by EDMM process, and if you see the enlarged view of this, you can see how many features have been created, complicated features have been created in terms of few microns. So, this particular process is very good. So, you can see how complicated these features are which have been created by micro EDM process, as you can see over here. Now, here this is really the micro mixer. So, micro mixer kind of the thing have been created over here, so that the fluid microfluids or mixing can be done over there. Here is 0.52 millimeter diameter extrusion die which has been created by micro EDM process. It is exactly 520 micron size die has been created over there, and you can see here ladder with 100 micrometer gap between teeth. This is the ladder being created over there, so that this is the 100 micrometer gap is there between the two. This is one ladder, another ladder, and so on. So, these kind of the ladders have been created, and you can see here are the gears, micro gears of 520 micrometer have been created over here, and this is the pin of 655 micrometer which has been created with the help of the micro EDM process. So, you can appreciate really that this particular process can be used for producing micro products, micro devices, and also micro components. Some of the examples I have already shown to you. Now, electro discharge grinding process is there. This is a hybrid process where scientists have combined electric discharge machining and grinding process to take advantage of both these processes and to get rid of demerits of both these processes. The question is, why do you need electric discharge grinding? Now, to grind very hard materials, first by softening it by the sparks which you are producing in electric discharge grinding process, and then grinding soft material, because once you have the spark, the hard material becomes soft, and if abrasive particle is coming behind the spark, then it will remove the material which is softer than the parent materials. So, you can see here, this is the wheel, this is the grinding wheel, this is the insulated spindle is there, and then dielectric, this is the dielectric field in the tank, and it is the workpiece which is to be ground, and you have the DC power supply over there, and workpiece is there, shifts are there which are produced due to the grinding, and rotating conductive wheel is there. The wheel should be electrically conducting. Now, you can see that when sparking is taking place, what is happening, that if a spark is taking place and behind is the abrasive particle, then this workpiece material becomes soft, and this abrasive particle will be able to remove the material from even very hard workpiece material. This is something like this, that if abrasive particle is here and sparking is taking place over here, then this material becomes soft. In this particular case, the abrasive particle has to be like this. So, when it is coming over here, then this abrasive particle will be removing the soft material, not the hard material which this parent material has the hardness. So, this is the advantage of this particular process, that you can first make the workpiece material soft and then remove it with the help of the abrasive particles. So, you are really making use of both the processes, EDM process and grinding process, to grind very hard material which are difficult to grind otherwise. Hence, electric discharge grinding process is very useful from that point of view. Now, we will see applications of electro discharge grinding process. One of these applications I have already told you, for producing the electrodes or very thin wires in terms of few tens or few hundreds of micron using this particular electric discharge grinding process. And you can see this is the this is the kind of the wire or pillar has been produced by this particular process like this. So, which you cannot produce otherwise by either EDM process or alone grinding process. Wire EDM process, let us take the applications of wire EDM process. Electrical discharge machining, wire cutting is a thermal mass reducing process that uses a continuously moving wire to remove material by means of rapid controlled repetitive spark discharges, which happens in EDM process also. A dielectric fluid is used to flush the removed particles, because when melting is taking place, they get the molten material gets solidified and debris are there and they have to be removed. So, these particles are removed or flushed out, regulate the discharge and keep the wire and workpiece cool. So, these are the basic functions of the dielectric in the wire EDM process or EDM process in general. The wire and workpiece must be electrically conducting, that is the basic requirement. You can see here the microstructure made with the help of the wire EDM process. You can see all these dimensions are in microns. So, it is really difficult to make such kind of cavity without wire EDM process. Even with simple EDMM process or electric discharge micromachining process, it is difficult to make. So, wire EDM, wire electric discharge micromachining process has its own important place in the advanced micromachining processes, and it is very simple. As you can see over here, I will just explain you quickly. This is the workpiece and here is the dielectric being supplied, and this is the wire which is moving from this pulley coming out and being rolled over this particular pulley. Now, you can see in large view of this, here is the wire and here is the workpiece. So, there is always a gap between the wire and the workpiece surface, and that gap is known as inter-electrode gap, and it may be different at different locations, and because of sparking material is removed and you are continuously feeding either the workpiece in this direction or the wire in this particular direction. If you want to keep the wire stationary, then you have to feed the workpiece in this particular direction or in this particular direction, depending upon your requirement, either in this direction or in this direction where you want the cutting to take place. This way you can make use of this wire EDM process. Thank you very much. We will continue with this in the next lecture. Thank you.